Hello, students of science. Let's talk about an activity series and what that is. So, the fact that you can write a chemical equation doesn't necessarily mean a reaction will take place. I could, for example, say this reaction here, sodium hydroxide plus silver nitrate is going to make sodium nitrate and silver hydroxide. I could make that up. I don't necessarily know that is going to take place. To determine whether or not it's going to take place, that's when I'm going to use this little thing here to the right called an activity series. When I do that, I know that this will take place and I will see this reaction between sodium hydroxide and silver nitrate, making that silver hydroxide precipitate that we have there. An activity series is going to help predict if a chemical reaction will occur. So I need to use this activity series, very much like the one that you actually have in your notes, to figure out whether or not this reaction will take place. You're going to have something similar to this in your notes, so please follow along here and then I'm going to have you copy down. We're going to take a look at this first series of metals. Lithium, rubidium, potassium, barium, strontium, calcium, and sodium. All of those are going to react with cold water and acids. This next one here, from magnesium down to cadmium, they will react only with hot water, steam, and acids. This next one down here will not react with water. So you can see we're already going down the list, less and less reactive. This one will do cold water, which is, fairly unreactive. This one only hot water. This one won't do it at all. Still reacts with oxygen. This down here will only react with oxygen, and these ones down here, silver, platinum, and gold, also known as the precious metals, are fairly unreactive. Not a coincidence. So, in your table, I want you to sort of mark these down here, lithium through sodium. They will react with cold water, acids, and oxygen. Darn near everything. From magnesium to cadmium, only hot water, acids, and oxygen. So these have to be pushed a little bit more to make react. This next section down here, only acids and oxygen, so they still react with acids. Down here, oxygen only, and these ones down here, nothing. So this is what I want you to actually copy down into your table. Cold water, hot water, acids, oxygen, nothing. So most reactive, least reactive. The way I've been thinking about this is, let's say these ones up here, lithium through sodium, these are Ryan Gosling. Hey girl. Very reactive. When it comes to a chemical equation, these ones here, they kind of have their pick of it. Whereas we get down to the stuff down here, silver, platinum, and gold, kind of the Steve Buscemi, great actor, no disrespect if he's watching this. He is not. But not really reactive. So when it comes to it, think of it as almost like going to prom. Let's say Ryan Gosling arrives by himself. One of these lithium or potassium or sodium on their own. They arrive without a partner. Whereas you see Steve Buscemi show up with a date. There's a very good chance that whoever is going with Steve Buscemi to that dance is going to leave for Ryan Gosling. The higher it is up here, the hotter it is, the greater chance it's going to steal your girl, your element. So let's take a look at a couple examples. Zinc plus water in the liquid form at 50 degrees Celsius. So 50 degrees Celsius, that is going to be cold water, not steam. So let's take a look. Will zinc react? If I find zinc on here, this is only going to react with steam, not cold water. This one will not have a reaction. The water is not hot enough. So if we find zinc on this one here, it's not hot enough to completely replace that. Let's look at tin and oxygen. If I find tin, tin is going to be right here. Tin will not react with water, will react with acids and replace hydrogen, and it will react with oxygen. So right here, we know that this one is going to react with oxygen. And there we have it. Cadmium plus lead nitrate. So here we have an example. Will cadmium steal lead's date? So lead is here with nitrate. Is cadmium hotter than lead? Will cadmium walk away with the date? So I'm going to find cadmium and lead right here. Here's cadmium, Cd. Here's lead down here. Cadmium is kind of like the Ryan Gosling. Arrived by itself, but is totally going to steal lead's date because, let's face it, lead kind of looks like that. So in this case here, cadmium is going to steal the date. We got ourselves a reaction. Next up, copper and hydrochloric acid. If I find copper right here, we see that that reacts with oxygen, forming oxides, but it will not react with acids. So no reaction will take place there. Nickel plus water in the liquid form. So let's find nickel on here. Nickel will not react with water. Doesn't even matter the temperature. No reaction going to be happening there either. Next up, gold and hydrochloric acid. I don't even need to check this one. We know that these precious metals down here are fairly unreactive. That's why they're so precious. They're pretty much always going to stay that way. Gold plus hydrochloric acid, not going to do it. cadmium and hydrochloric acid. So now, same thing, I'm looking at an acid, but I gotta find cadmium up here. Cadmium will react with steam and acids. Ooh, so we know it's going to react with acids. We got ourselves a reaction. And finally, magnesium and cobalt. So once again, we have these ones arriving with a date. Magnesium is by itself. Cobalt is got a partner. It's got a date. The question is magnesium hotter than cobalt? Will cobalt leave by itself? Let's check the table. Here's magnesium right up here. Let's check cobalt. Cobalt is down there. Magnesium, way hotter than cobalt, way more attractive. Magnesium may have arrived by itself, but it ain't gonna leave by itself. We got ourselves a reaction. So right here, pretty much everything below silver on here, not gonna react. Everything above silver will react depending upon the circumstances, whether it's oxygen, acids, hot water, or even, cold water, because even cold water right here, enough to get these going. So let's take a look at a couple others, where they're almost exchanging dates. Iron plus copper sulfate. If I find iron on here, remember, the ones toward the top are our Ryan Goslings. The one near the bottom are Steve Buscemi's. Again, excellent actor, don't mean to bash him at all. So let's take a look. Iron, we're going to find right there. Copper, we are going to find way down here. Iron, way better looking than copper. We are going to have a reaction there. It's going to steal the sulfate there. So there, I'm going to have a reaction, and I'm going to form solid copper and iron sulfate. Let's look at the next one, aluminum and iron oxide. So I'm going to find aluminum right there. Iron, of course, we know down there. Aluminum, more reactive, more attractive than iron. Going to steal iron's date. Got ourselves a reaction there as well. Next one, magnesium plus copper sulfate. Magnesium right up here, fairly reactive. Copper, much farther down, fairly unreactive. So once again, magnesium, way better looking, more reactive than copper down there. It's going to steal the date. We're going to get ourselves a reaction forming copper and magnesium sulfate. Now, what's the application of this? Not everything is just looked up in a table. The table is built from a lot of things, but it has one very, very useful thing. I know when things are going to react. For example, steel, whose main component is iron, rusts outside. So what they're going to do is they're going to use something called galvanizing. Galvanizing is a way of protecting steel by putting zinc on the outside. Why zinc? Well, zinc is more reactive than iron. All of these, potassium, sodium, lithium, calcium, magnesium, aluminum, and zinc are more reactive than iron, whereas copper, silver, and gold are going to be less reactive than iron. Iron is the main ingredient in steel here. You want to coat it with something that is more reactive. If you put something that's less reactive on the outside of it, the iron will still rust. If I put something more reactive on the outside, this is going to react and almost break down to protect the iron underneath it. So zinc will resist corrosion, but even if it's exposed, the zinc is going to quote-unquote rust before the iron or steel will. The zinc is almost sacrificing itself to protect it underneath it. All these are going to want to react before the iron is. They will all almost sacrifice themselves for it. Now, you wouldn't want to coat iron in potassium. That's almost too reactive. Potassium literally explodes and catches fire with water. You don't want to be using galvanized nails that will catch fire in the rain. So you want something that is going to be more reactive than iron, but obviously not too reactive. That's why they use zinc, just above it on the activity chart. A sacrificial anode for iron should be made of something more reactive than iron. Something less reactive would not break down until long after the iron rusts. So magnesium, aluminum, and zinc are our most common sacrificial anodes, the three of them that are directly above iron in our activity charts. This ensures that anytime you have steel exposed, if it is coated with these will rust, these will react long before the iron does, protecting the iron and the steel longer. This is how you protect things when they are left outdoors exposed to the elements. Galvanizing them exploits the activity series to protect them and make sure that the iron stays stronger longer.